was saying, and he will tell us about cubulating small cancellations and free products, and they cubulated with Teddy and Daniel.
Okay, terrific. Yeah, thanks. Thanks to the organizers for the opportunity to speak, to be here. It's been having so much fun. I mean it. Okay. So, where do we begin? That is X for exercise. So last Thursday, Nir told us about how to take a group that has, you sort of take a partition of the generators, and you can build these non-residually finite groups. Okay, so here's one. Take the first three, make them generate SL3Z. Take the second three, generate this Artin group. This exercise is not relevant for the talk, it's just for fun. And then add one relator, this one. Okay, and the question is it residually finite? Okay. Okay. Great. It is residually finite. Okay. In fact, if you take these, I'm splitting the group into two parts, A and B. And if A is any, A and B can be any residually finite group. And then the same conclusion will hold. Okay. So that's going to be sort of a consequence of the thing I'm going to talk about today. So just to have like a example to have in mind and sort of see where we're going, I should mention that maybe if the only way you know how to build residually finite groups after last week is to take a hyperbolic group that's cubulated, then you don't need anything I'm going to tell you. Okay, so first, let me just mention, start at the beginning, that in 2014, Alexandre Martin showed that such a group would be, if you started with A and B hyperbolic, okay, if A and B are hyperbolic, then this quotient, let me give it a name. Okay, G bar is okay. G bar is okay. Then G bar is again hyperbolic. Great.
What are the G bar? Like what?
G bar is that relative presentation. I start with two groups A and B. I plug them in here, and I add this one relation.
Do they have like any triplet elements?
Okay, you have to have an A and a B. They need to be true generated. Yeah, at least they should have an A X and B Y should make sense. These are commutators. Okay. Thanks. That's good to clarify. I'm trying to sneak things under the rug, and I guess it's good not to let your PhD students do that, right? Yeah, but you've been trained for 6 years. You can't help yourself. So then in subsequent work, Martin and Steenbock said that if A and B are that group, no, it's not that one. No, he didn't study that. I'm going to state it. It's coming. It's coming. If A and B are cocompactly cubulated, here's a hint. Okay. You knew that. Yeah. G bar is cocompactly cubulated. Okay. So if we get these things, then we have that. Hence, if you were here last week, you know that G is residually finite. Why? Because it's virtually special. That's the only way I know to show that that's residually finite. The G bar is the combination. Yeah. It's both. Oh, sorry. Yeah, sorry. This was under the assumption I should add this before this line. Insert here that A and B are hyperbolic and cocompactly cubulated. Sorry. Yes. Thank you. That's a good, important clarification. Okay. Good. Let's see our main result, and then you should understand what they did. Wait. Hang on. Is that does that fit into your work with Donnie? Does not? I'm gonna put you anyways. Okay. You can cubulate in there's two ways, right? So great. Okay. No. Here's the main theorem. This is joint with Einstein. Yeah, there's two papers. One is joint with Teddy and one is joint with Daniel. Maybe I'll get around to talking about the second paper. Here's how it goes. I start with two groups, A and B, and then suppose that they're both relatively hyperbolic. Okay. And then suppose that both are relatively cubulated. Okay. So you guys are dying to know what that means. So you should go to Teddy's talk on Friday. He'll tell you all about what that is and what the consequences are. It's a very nice cocompact action on a cube complex, typically not proper. Okay. I never know what to do. Logically, it's I prefer if it's if then, right? As if then any C prime 1/6 small cancellation quotient, we'll give it a name G bar, is relatively cubulated. So that's right. So this small cancellation quotient will be of the form A free product B quotient by some set of relations. And these set of relations will satisfy this small cancellation condition. Okay. Get to that in a moment. I think I was inspired to write larger than I've ever written before in my life. Let me over here list a corollary of that theorem, which is that suppose that A and B are both residually finite, then you can use this theorem and work of Teddy and Daniel Groves to show that G bar is again residually finite. G bar meaning any C prime 1/6 small cancellation quotient. Yeah, great, good parsing. Okay.
Right board now the same as the G bar on the left board?
Yeah.
I'll take two blackboards.
No, because these are assumed to be hyperbolic and cubulated. And this is not hyperbolic and this is not. Small cancellation quotient, yes. See, G bar will always be my secret symbol for a small cancellation quotient because it takes that long to write it. Okay. Which groups? This group is relatively cubulated, yes.
Those groups do not like the A and B don't.
Oh, sure they do. They are. They are.
Well, they are relative.
Go to Teddy's talk and find out why Teddy can't tell why any finitely generated group is relatively cubulated. That's the secret. That's the secret sauce here, that any finitely generated group is relatively cubulated. Here's your hint. Okay, you can get another hint. That's a cube complex. A point. Okay. There's also all kinds of stronger separability results than residually finite. Yeah, finitely generated residually finite. Start with any finitely generated residually finite groups, A and B. Then you take a small cancellation quotient free product. Yeah, okay. Let me say, Martin and Steenbock were working exactly in this setting of small C prime 1/6 free products. And that's their result. Their result is that you start with something cocompactly cubulated, you get something that's cocompactly cubulated. Also, there's a properness assumption here, right? Cubulated to me means properly cubulated, which is different than the setting here. So we have to deal with improperness. Corollary of the main theorem. No, okay, yes. See Friday. It's not clear. Yeah.
A and B, so PA and PB are just A and B.
Correct. Okay, let me let's write that.
And you're saying,
Yes.
that it's finite, see Friday.
Correct. This acting, okay, I'll write it now. No, yes, is a relative. Great, I think you understood. I was writing, so I couldn't listen. I couldn't multitask. Okay.
Just have my free product.
Yeah.
You are finally generated there.
Relative to the PA and PB.
I guess you don't want to say relative to what.
With respect to, thank you, this is an important point. The union of these two peripheral structures, original peripheral structures. Okay, yes, good. But right, like that is one way to interpret this. Start with whatever groups you like. Take a small cancellation product, it will act relatively geometrically on a cube complex. Okay, you don't need to know what the groups are. That's sort of the whole point of why we can prove this corollary. Okay, good. Good morning, I'm awake now. Okay, so my plan is to take some time to describe small cancellation over free products, and then see why it's sort of a natural place to study relative hyperbolicity. And then, depending on how much time is left at that point, I'll say some words about how to try to cubulate or relatively cubulate. Okay, so what's the start setup? Let A1 to AN be finitely generated. Okay, so then the free product, the fundamental group of a certain complex. Okay, sorry, I really like this sort of geometric construction for sort of what am I going to do? The small cancellation theory is going to give us a geometric model for all groups, all such groups G bar. Okay, these kinds of quotients. Okay, and I love this construction so much, so I have to give it to you guys. Of some complex, let's call it Y. Okay, so how do we build Y? You start with a star. Okay, 1, 2, N. Yeah. And then what I want to do is I want to attach to each leaf of that complex some, let's say you could pick a classifying space, any space that has fundamental group AI. Oh, I need another color. You may notice that I only wrote A and B in the theorems. That's because indices are really hard for me. But everything that I say works for more than 2 factors, 3 factors. Okay, good. In each of these spaces here, I drew them as circles. So that's a loop. I'm secretly here thinking of all of these being the integers, just for the purpose of the picture. Yeah, we're happy? Okay. Maybe I shouldn't put small cancellation here yet. A quotient is pi1 of some complex Z, which I obtain from Y by attaching some disks to this picture here, union disks. Okay, so let's try to imagine that example there. Hopefully I won't regret this decision. Okay. A squared x b y. Figure out the orientations based on your favorite way to write commutators. And I join each of these by a y edge. Okay. And in fact, that y edge I should subdivide with the center of the star. Okay. This is what it looks like to take a disk and label it by some word in the free product. That's from the normal form on free products. Okay, it's all coming from Bastier theory. Okay, so we have this complex Y, we have this complex Z, and we want to somehow build a space on which they act. So you take the universal cover. Okay, great, huh? That is a tree of spaces, the universal cover of this space, this guy. And here you get sort of something like that. Right, so here's the tree of spaces. The lift of a circle is lines. We all know that. And here there's this disk that's been glued in here. Okay, so you should imagine maybe like this red line got identified with this one. And that closed up some loop, and we fill it in with a disk. Okay, so this here is Y tilde. This is Z tilde. I'm trying not to say complexes of groups. Oh, well, I'll say complex. So so this Z tilde is really like, that's a great geometric model for these quotients G bar. Okay, the group will act on it. We kind of built it. If you started with these spaces here coming from, say, Cayley graphs with respect to a finite generating set, the whole group's going to act freely, cocompactly on this complex Z tilde. Okay, but kind of you see a lot of the factor groups. Okay, so what I want to think about is you can take this space and right. So what happens here in this tree of spaces? You can imagine collapsing each vertex space. Okay, what do you get? You get the Bastier tree. Okay, each vertex space, universal cover of the vertex space over there becomes a point. Right? Now, we do the same thing here in Z tilde, and what you'll end up with is a 2 complex. Collapse universal covers of vertex spaces. So you start with Z tilde, and I'm going to collapse onto a 2 complex. Okay. And what's that correspond to? That corresponds to collapsing these colored edges down to points. Okay, so let me see if I can draw that. And if you really want to think about how to sort of you love labeled disks, you can imagine labeling the corners, okay, by the edge that you collapsed. Okay, everyone is good. Interrupt me lots. I'm expecting that. That's fine. It's better for everyone. And we've memorized this. Great theorem. Friday, go to Teddy's talk. Okay. All right. So that's just a quotient so far. So what makes it C prime 1/6? I have to define a piece. Right? A piece is trying to measure. I take 2 disks and I want them to overlap for a very small amount. Okay, so let's describe a piece. And I need to make an assumption here, which maybe those of you who had enough coffees this morning understood from this picture, is that every relation that I'm choosing in this relation set, right? This is the relation set. Let me just recall here so that everyone has it. I take a free product of 2 groups, and I'm taking a quotient. Okay. So every relation is loxodromic on T. I didn't define T, I realize. T is what happens when you collapse this to a tree. Okay, collapse those vertex spaces. Okay. Yes.
Okay. Here's where my from. If I had some of these,
Yes.
I could maybe not collapse them.
You could not collapse them. Yeah, you could do that. That's allowed. Wait. Okay, but in the construction of X, I collapse all of them. All the vertex spaces become points. You're free to do that, but then you're not proving our theorem. Yeah. I don't want to be too controlling. A piece is a segment in T that is common to axes of two elements R and S in
Doing the whole way through, I could just show you it's like the little piece of the polygon, but the little corner things have to agree or something.
the corner things should agree. Yes, the labels, right? So now we want to work down here. This is Riley's ready. Huh? You start here and you look at an overlap. Okay. Hexagons. Okay, hexes 7. That's fine. I'm going around this vertex, and this transition here corresponds to some element of the green vertex group. This transition over here is a different element. So if I'm trying to not write things out in words. This is what I love about this construction, which is mostly it shows up in earlier work of Martin and then Martin Steenbock, is just how geometric it is. You don't have to write out normal forms or twisting elements or small category without loops. I mean, they do, but right. Okay, so those are different things. We're right here. Here you could think of syllable length, and you're counting pieces with respect to syllables. Okay, great. Okay, good. So we have a piece. Okay, and so then of course we need to now have our small cancellation condition. R satisfies C prime 1/6, that condition, if for every relation, the size of a piece, the ratio of the size of a piece in R to the length of R, what do I mean by that? I mean the translation length of R in the Basser tree. That's the free product length of that, of the normal form of R. Okay. I need that ratio to be strictly less than 1/6. Okay, you can define 1/p the same way. That's a geometric small cancellation. Path length in the tree, right. I should mention, that's good. Here we had this lovely space Z tilde. I collapsed for some reason the vertex spaces. What if, okay, everyone understood that these were subdivided. Do it here. What if you collapsed here the lifts of the star everywhere, right? What happens in the base space here? Right, we get one vertex, and if we took here calligraphs of the vertex spaces, you get a relative calligraph of the quotient G bar. Okay, if you know what those words are. Okay, so there's sort of you could try to define translation length in the other collapse in the calligraph, and then you get what's classical small cancellation theory that Nima told us about last week. You guys are doing great. Okay, so we've done small cancellation, and so now in my notes I have big consequences. So let's start with a result of Wise in 2004. What's the story here? The story here is that there, these guys, right? And what am I thinking? I'm thinking that A is hyperbolic relative to some collection PA, and B is hyperbolic to some collection B. Okay. So Wise said that if these two peripheral collections are equal to each other and nothing, what does that mean? That means that A and B are themselves hyperbolic groups. Then G bar, a C prime 1/6 small cancellation free product, is cocompactly cubulated. Okay, that is really inspiration for a lot of what I'm talking about. Oh, let me fix the statement. That's a lie, right? That's not due to Wise. Excuse me. if A is equal to B is equal to Z. Yeah. Sorry, free groups, quotients of free groups. This is classical small cancellation theory. The statement is you take a C'(1/6) group, and then you get cocompactly cubulated. Excuse me. Thank you for that, catching that. That's where it's coming from. You know, oh, I'm erasing the picture. Great. Let's talk after, and you guys can call me out for lying to the room. Good job. So I found out that there's something. Sometimes you like start playing with these disk diagrams and just end up proving things that people proved years and years ago. Right. So there's a natural map which starts with A star B. Okay, I never did this for you guys, but in my notes that's G. That's why we don't have G bar. Okay, and you have this natural map from G to G bar. Sorry about that. Rho restricts to an embedding on factors A and B. Okay, so I take this is a consequence. Sorry, C'(1/6) implies that this under this quotient map, your vertex space is embed. That's actually the reason that we could do this collapsing map over here. Okay, we didn't have the red and the green getting all twisted up and doing crazy things. Okay. And then maybe I don't know. There's the next thing is in Linden and Shoup. But maybe it was known before, which is that I want to say X. Oh, yeah. I want to say that the Cayley graph of G bar with respect to the generating set, all of A and all of B. I should write that as a union. Okay. This satisfies a linear isoparametric inequality. I heard sounds of affirmation from the audience. Ask that person to talk more about that in the break. Great. What again, this is C'(1/6) implies that this Cayley graph has this linear isoparametric inequality. Great. So now, if we're observant and you studied enough of your relative hyperbolicity, we have this kind of useful lemma that G bar is hyperbolic, not exactly on the nose, relative to, okay, hang on, relative to A and B. That's the thing that comes immediately from this statement here. But if A and B are themselves relatively hyperbolic, then I get relative to the union of the peripherals of the vertex spaces. Great. Nodding. Okay. So you have this space relative Cayley graph. We have the space X. We would like to, for our purposes, one of the maybe to me was kind of challenging getting into relative hyperbolicity was that there's a lot of different definitions. And then there's the terrific work of Chris Pruska showing that they're all kind of, well, like many people, Bowditch, Ozen, Pruska, they all work, okay? But you have to say why they work, and right, you have these different collapsings. You have X. Oh my gosh, they're all everything's. So who's going to tell you that everything's fine? In 2007. Charney and Crisp were studying relative hyperbolicity in Artin groups, but Ruth Charney and John Crisp, I think John is the first name. So each collapse that I've just described in this construction is a G equivariant quasi-isometry. Okay, let me try to parse. Is that you can take Hang on, hang on. Let me just draw an arrow. I think it will make everything better. Okay. I'm going to define a map from X to this. Well, how do I define that map? X, uncollapse, blow up the vertices, and then collapse back down to the relative Cayley graph. This is a G equivariant, G bar equivariant quasi-isometry. And so that's like, at its face value, right? Like, okay, you have these different actions, but really what happens here when you have a quasi-isometry, you can work with whatever space you want. So for example, Ozan said that the action of G bar on this space is an acylindrical action. Okay, you pass it through an equivariant quasi-isometry, you get an immediate corollary is that G bar acts on X acylindrically hyperbolically. Acylindrical. It's an acylindrical action, and X, because it's quasi-isometric to a hyperbolic Cayley graph, is now hyperbolic. Okay, great. We have an acylindrical action. If you were here 2 weeks ago, that's not 2 weeks ago. However many weeks ago, it's been. Say how much fun I've been having here. Oh, it's like it's too soon. That's what we want, right? Acylindrical actions are really good. Why are they really good? For me, they're really good because if you look at convex subsets of X and you look at their orbits under the group, you can't have too many of them fellow traveling. Okay. That's sort of a consequence that's sort of written down very nicely by Abbott and Manning. Okay. Okay. Where's the main theorem? It's hiding. It's gone now. There's something about cube complexes. I've said nothing about cube complexes so far. Let's fix that. Yeah. Any questions before I move on? I'm about to shift gears. That was it from small cancellation theory. So, cubulation criteria, right? So we saw how to. Who wants to know what a relative cubulation is? That's good. Okay, let's do it. Okay. G acts relatively geometrically on X, which should be a hyperbolic space, hyperbolic graph, let's say, just to make life simple. If one, I look at the quotient and that's compact. Okay, we start with a cocompact action. We need the green chalk. And then the action of G on X is, okay, line quotes, proper away from fixed sets of, okay, you don't just take any group. I mean, if you really like actions on a point, you do, but start with a group that's itself relatively hyperbolic, okay? This is only for relatively hyperbolic groups. So what happens is we want to define an action that's wants to be like proper cocompact, but its failure to be proper is coming from the peripheral subgroups that you started with. Okay, so you should imagine a group acting on a space like a Basser tree where it's not proper if the vertex groups are infinite, but the infinite stabilizers are all commensurable to your peripheral subgroups, the vertex groups. Okay. So that's relatively geometric. Relatively cubulated is that you act relatively geometrically on a cat-zero cube complex. Fixed set. Bounded orbit. Yeah, that's what I mean by. Yes. What? Sorry.
An actual proper action will, I think, satisfy you both, but I don't want that yet.
A proper action.
Of every purpose.
Yeah. Okay. Yeah. So okay, here we go. Good. Good job, Dave. Friday. These guys are, that's the easy, you know. They're the maximal isotropy groups. You guys didn't want that. Okay. So we saw how to cubulate using walls, and then Nir mentioned this. One of the ways to get an action on a cube complex is to use the boundary. Okay, so there's these boundary criteria. Let me write some names. To me, originally Bergeron and Wise, for hyperbolic groups, and then the formulation that I'm going to describe is for relative actions, and so then you should look at work of Einstein and Groves. We're doing on time. We're doing fine. And what do we do? If G is hyperbolic, so this is, I'm going to start with the statement of Bergeron and Wise, and then I'm going to play with it, such that every distinct pair, alpha and beta, in the visual boundary of G, it's a hyperbolic group, it has a boundary. There exists a subgroup H associated to those two elements that is, okay, space, quasi-convex, and codimension 1. Every pair of points, I separate them by one of these subgroups, then G acts on a cat0 cube complex, cat0 cube complex, geometrically. Sorry? You just pick groups? No, absolutely not. Thank you. What's this subgroup supposed to do? It's supposed to separate alpha and beta. Yeah. So such that I see crane next. I'll put the condition goes up here. Boundary of H separates alpha and beta. Then this action, you get a geometric action. Okay, that's Bergeron Wise. We want a relatively geometric action. So we start with a relatively hyperbolic group. Okay. And then you want to take distinct pairs in what's called the Bowditch boundary, the relative boundary with respect to this peripheral P. And then you want these subgroups to be relatively quasi-convex and something called full. And then you don't get a geometric action. You get a relatively geometric action. Great. That's the boundary criteria. That's what we want to use. Let's try. Maybe while I'm erasing, what's?
Can I ask?
Yeah, please.
A question?
Yeah. I don't have to.
Aside from this extension of the boundary criterion, do you know of other extensions in other contexts? I'm just curious.
I want one. I don't have one though. You're gonna do it? You're gonna curtain boundary? Do it. Okay. What's the important thing in the boundary criteria is that you have to be able to find these subgroups. Okay, to find those subgroups, I need some way of finding relatively quasi-convex subgroups. You also need to certify that they're full, but if you want to understand what full means, I won't do it. Everyone understood. I'll just draw the arrow. Right there. Everyone, great. So let me start with just a way of finding quasi-convex subgroups, relatively quasi-convex subgroups. So this is a theorem of Martinez-Pedrosa together with Wise. And there's a slight generalization that we developed with Daniel Groves, which goes as follow. I think I'll need this to look at to get the statement exactly right. So if X is space fine, if you don't know what fine is, that guy's fine. That's why it's named X. With respect to some relatively hyperbolic structure, and H is a subgroup of G satisfying the following conditions. Okay, one that I need is that H stabilizes some set C inside of X. I want so what's the conclusion? The conclusion is going to be that H is P relatively quasi-convex. That's the point. I want to study everything geometrically. So I want to start with a quasi-convex subset, okay, that's being stabilized by the subgroup H. I want H to act on that complex, and I want that to be cocompact. Okay. And then the third condition, which is a consequence of what happens because I've left a blank, right? Here, if you have a fine graph, your peripheral subgroups are fixing points. They're vertex stabilizers. They're not doing anything with edges. Okay. But you could imagine in between X and Z tilde, I could blow up these vertex spaces ever so slightly to be, say, finite graphs or some finite cube complex, something like that. Okay. And then maybe you don't just have peripheral stabilizing vertices, but you get peripheral stabilizing bounded subcomplexes. Okay, this is something we call it a generalized fine graph, fine action. And so what I want, maybe I'll just draw a cartoon, is that if I look at this quasi-convex subset, here it is. Maybe it looks like a tree. And it intersects one of these peripheral subcomplexes. All right, so this is a subcomplex that's being stabilized by some peripheral subgroup. And when you have this non-trivial intersection, then H intersects that parabolic has an infinite intersection. You want this condition. Okay. Suppose you can satisfy these three things, then you get now a recipe for cooking up relatively quasi-convex subgroups. And let me mention that, right, this result is sort of like, it's more technical, but the point is that all of you have your favorite relatively hyperbolic groups. Hopefully it's not just a group acting on a point. And you can try to cubulate it. Okay, and you can try to cubulate it by finding a nice action on a graph, and trying to separate boundary points using these criteria. Okay, so let me just mention some very recent work of François Dominy and Suraj Krishna. I won't get the statement exactly right, but you should ask François about it. But let's see, how do I want to say it so that, okay. Look at free products again. Okay, they're not going to do small cancellation theory. They knew that was already done. But what they want to do is we're just like, I'm in the business of just building groups. You start with something you like and you make it slightly bigger. If you free bicyclic group people, you love this thing, right? Take phi to be in the automorphism group of this free product. Okay. And let's see. I want to stabilize the free factor decomposition, and it should be relatively irreducible and relatively atoroidal. Many what? I need another free factor. Are you sure? I think 3 is enough. I think that they say 3 is enough in their paper. Yeah. Many. There's lots of these. Okay. Hopefully more than 0. This mapping torus group is relatively cubulated. And what do they do is that the free bicyclic case was already, those are, when that free bicyclic group is hyperbolic, we look to this side of the room, and Hagen and Wise showed that. So maybe I should, yeah, this is building on work of Hagen and Wise for free bicyclic case. I forgot to look up the year on that. And then they argued that this is cocompactly cubulated with proper action, I think. Infinite dimensional? Hyperbolic case, you're okay. Okay, good. So this is a relative version of that result. Okay, they have to do a lot of work to build that space, but then at the end of the day, it boils down to pick points in the boundary, find separating subsets, and then apply a boundary criteria. Win. Okay, great. How much time do we have? Exactly enough. Exactly as much as I have. Oh, all right. Let me, in the last little bit, let me give a very quick sketch of how to separate boundary points. Draw a picture. Let me erase this here. Let people try to come up with the proof in their head. I erased X. Oh no. Okay, it'll be fine. We'll have to survive. I'm going to pick 2 points in the boundary not equal to each other, alpha and beta. Okay. And then I want to join them by some bi-infinite geodesic.
In the boundary, I mean, oh, sorry, in the space?
In the space. Sorry, this picture is happening. I mean, okay, I have these things. So this is, where should you imagine this picture? I didn't describe the Bowditch boundary of these groups. Okay, let me say. We have, what's the setting that we're working in? We have a group G bar. It's acting on a space X. It's a 2 complex coming from collapsing the vertex spaces over there. And that action, so from the action, I get a description of the boundary. Let me just explain what the boundary is in terms of points. Okay, as a set, the peripheral boundary, okay, so this is with respect to the peripheral structure A, B, the entire A and B. I'm collapsing the entire vertex space of G bar is equal to, as a set, there's a very interesting topology on this boundary. The boundary of X, okay, I get all the visual points in the boundary of X, but I also get points from the peripheral being stabilized. So as a set, this is also the 0 skeleton of X. Okay. Okay, so in my picture, let's imagine that both alpha and beta are on the boundary of X. The argument is not so different. You look at this such a geodesic, and now this is inside of maybe X bar, union its visual boundary. Right? I have hanging off of this geodesic some 2 cells, some polygons. Okay. Okay. So if I've drawn like all the polygons bordering that path, I'm thinking of this as a path in the 1 skeleton. I want to separate points. Well, how do you try to separate points in a 2 complex? Well, hang on. Where's that space? Oh, I've erased it. The space Y. Oh, all the white chalk is gone. It's hiding inside of cubes. Y was some space that was built out of a star. And I collapsed all the colored vertices, so all my polygons are even-sided. So every edge has a well-defined opposite. Okay, let me try to draw that picture here. I take an edge, right? Every edge has one side which is the center of the star. And because it's even-sided, there's some other edge on the other side which it can be paired with. So try to do that. So take the midpoint of that edge and join it with the segment across each polygon. Okay? And then what do you want to do? You want to separate things. Well, that's only separating inside the polygon. So you want to extend out of each adjacent polygon. So if you have any other polygon that shares that same edge, I want to also extend this through here. Okay? Right. And maybe you have branching. Okay? That I'm imagining that disc coming out of the front. I'm not a knot theorist. Right? You extend to every polygon that touches that edge. Okay? Keep extending, make this thing maximal in that sense. And then hope that somehow that's going to be the quasi-convex subsets that you want to separate. Okay. Oh, okay, good. I'll make it. I'm gonna make it. Thanks. So what would you be happy with? You'd be happy with one of those things that looks like this. Okay. Right. But what do I need? I need the boundary of the subgroup that's going to correspond to the boundary of the subset, okay, to separate alpha and beta. What would be the horrible situation? Would be that you cut through somehow your polygons, and then what if your subset did this kind, right? This is a geodesic, that's a nice convex subset. What if this hyperbolic, sorry, not hyperbolic, this convex subcomplex stayed within bounded distance of the geodesic alpha to beta? Well, then it's not separating because alpha and beta are in the limit set of the whole complex. Okay. So now what you want to do is you want to say, well, there's infinitely many of these that cross, and acylindricity says they can't all be close to each other. So there exists one that will cut straight across, and you'll be very happy because you've satisfied your boundary criteria. Thanks for your time.
So if A and B are relatively near blocks, you do something like intermediate block.
Right. Yes. I've secretly only worked with the peripheral structure A and B. Right. So what you need to do in the other case is that there, I don't collapse the entire vertex space. I replace the vertices of this X with cube complexes that the vertex group acts on. Okay. And then what happens is you need to be a little bit more clever because, and these ideas are well developed in Alex Martin and Marcus Steenbock, and then also Pasha-Yankiewicz and Donnie Wise, where you have now vertex spaces and you have to extend hyperplanes through a vertex right. You have hyperplanes in the vertex cube complex, and those will extend into your disks, and you hope that those are quasi-convex too.
We're trying to calculate the quotient of a free product with more than two things. You might not have an opposite edge. So what do you do?
You don't? Well, so I started with a star, right? What's a, yeah. I'm looking at words that are loxodromic on the tree. That means it does something over here, and then it comes back through here, and then it does the next vertex space. Okay, but I collapse the vertex spaces, so it's still an even-sided polygon. It doesn't, but whatever the length is, it's 2 times that, the length of this path in the Bastier tree. That's the reason for this very sneaky graph of groups decomposition.
Have a question or just say hi to me?
Oh, okay. Okay, so I guess, yeah, let's thank Thomas again.